Hello everyone, welcome to my first video. This is how to solve Leetcode 142 linked list cycle 2. There is of course a lot of tutorials on this already, but none of them really explains where the Tortoise and Hare algorithm comes from, so I thought I would do a full explanation of this problem. Now, if you haven't solved linked list cycle 1, I highly recommend you do that first because this is an extension of that problem. Right, let's go through it. Given the head of a linked list, return the node where the cycle begins. If there is no cycle, return null. There is a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer. So looking at the diagram given below, your code should return node number 2 since that is the start of the cycle. Now let's look at the diagram. I've drawn them without numbers for ease of understanding. Let's label the entry point with the letter E. And the distance from the starting node, the head, to the entry point will label as x, and this is the number of steps. Now, if you've solved linked list 1, you'll know we use a fast pointer and a slow pointer. And when they meet, you know that there is a cycle. So likewise here, we have a fast and slow pointer, and the node where they meet will label with the letter M. And the distance between the entry point and the meeting point will be labeled as y. Finally, the rest of the distance from the meeting point back to the entry point of the loop or the cycle will mark with the letter z. So we mentioned before that we have two pointers, slow that moves one step, or in this case one node every time, and then a fast pointer that moves two steps or two nodes every single time. Now that all of our requirements and parameters have been laid out, let us try and derive some equations showing how many steps or the distance each pointer moves. First, let's do the slow pointer, and we can see from the diagram the slow pointer travels a total distance of x plus y. And now the fast pointer, we can see that it travels x plus n bracket y plus z bracket plus y again. Okay, let's slow down here and explain the fast equation because this is probably the point where people get a bit confused. N here denotes the number of times the fast pointer will travel around the linked list loop with distance y plus z. And finally, when it travels around the loop once, it ends up at the entry point. So you got to travel the distance y again to the meeting point. Now, some of you guys will probably start asking, why is there an n term for the fast pointer but not for the slow one? Because the equation implies that the fast pointer will catch up to the slow one before the slow pointer even manages to make a first run around the loop. That is a very good question. That's a fair question. Let's think about it. So the fast pointer travels twice the distance as the slow one. So if the slow pointer does one run around the loop, this means the fast pointer must have done double that, so 2 loops. Which means there is no way for the slow pointer to do more than one. The fast one will catch up because in the time the slow pointer did one run around the loop, the fast one would have done double that. With that understanding, let us continue with the equation derivation and see what insights we can get. So we know that fast pointer travels twice the distance as a slow one, which means 2x plus y equals x plus n, y plus z plus y. That's pretty self-explanatory. You can see why that is true. The problem wants us to find what the entry node is. So let's rearrange the equation as if we're solving for x, because that tells us the distance we have to travel to get to the entry node from the start. We continue with the derivation and we arrive at x equals n times y plus z minus y. Now the minus y here isn't very helpful because we're thinking of it in terms of a graph and distance, so having a minus there doesn't really tell us anything and we can't really see any relationships. So now let's look at the equation of what we have and see what more insights we can get from it. Let's think about the parameter n. N here must be greater or equals to 1. What does this mean? It's essentially saying that the fast pointer has to have traveled around the loop at least once before it catches up to the slow one again. And let's think about it. This is true because the fast pointer will for sure enter the loop first before the slow one, and the slow one enters after it. So the only way for them to meet again is if the fast pointer travels back to the entry point and then catches up to the slow one that way. With that knowledge, how can we manipulate the equation to take that into account? Since n must be 1 or greater, we can actually extract out a cycle. So take out a y plus z, and now the equation becomes n minus 1 x plus z plus z. And the equation still makes sense with respect to the question because we are finding out the absolute distance traveled, and having a negative distance doesn't make sense. But in this case, the equation is still positive because if n was the smallest number possible, which is 1, then we would just get x equals z. Now this is a very profound revelation because now the equation tells us that the distance from the head node to the entry point of the linked list loop is the same distance as the distance to travel from the meeting point back to the start of the loop. Alright everyone, I know this is very exciting, but hold your horses because some of you will be asking me, why is n 1? How do you know that n is 1? What if the fast node travels multiple times around the loop? Then your equation isn't x equals z. You have more parameters in there. And the equation doesn't stand, and the revelation is not so profound. Well, actually, the equation stands, and making n 1 just simplifies the equation for us to think about. But you're right. What if n isn't 1? In the scenario that the fast pointer travels around the loop more than once, this essentially tells us that the distance of x is very, very high compared to y plus z. Why is this the case? Well, x must be long because this means the slope pointer is dilly-dallying. It's taking a long time getting to the start of the loop, which means the fast pointer is just traveling around in circles, waiting until the slow one catches up. So yes, n might not be 1, but at the same time we have 3 other parameters that keep this equation true. I know some of you don't believe me, so let's run through a quick example to prove it. Okay, both pointers start at the head node, and off they go. The fast one is traveling at twice the speed, twice the distance. It goes around the loop, waiting for the slow pointer to catch up. And there we go, they meet. Okay, now we can sub in our values of x, y, z, and n. And there you go, we see that the equation stands. Right, we have now basically derived the Tortoise and Hare algorithm, or otherwise known as Floyd cycle finding algorithm. How does this help us solve the coding problem though? Going back to the diagram, let's take a look. We run through the algorithm as before with linked list cycle 1 until they meet. Now, what happens if we reset the slow one back to the head node? And instead of making the fast pointer travel 2 steps at a time, we change that to 1. So same as a slow one. And then we let them traverse the linked list again. And when they meet for the second time, that is our entry node E. That is the answer we want for this problem. Now, the final question some of you guys will ask me is, why are we changing the fast pointer from 2 steps to 1 step? Because doesn't it need to travel around the loop multiple times? We are changing the behavior of the pointers and therefore the equation doesn't stand anymore. Well, no, because the fast and slow pointers have already met once. The fast pointer has already traveled through the loop however many times it needs, and it's already met the slow pointer. The equation has already been satisfied, And all we're doing now is using the insights of the equation to solve for the problem. So we reset the slow pointer back to the start. They travel step by step. And when they meet again, the slow pointer has traveled distance x and the fast pointer has traveled distance z. And since distance x is the distance from the head node to the entry point, we know that when they meet again, that node will be the entry point node. That is the difficult part done. If you understood all of that, then great. I'll give you time to try coding up the solution for yourself. But if you just want to see the solution right away, then here it is. Let's analyze the code now. Lines 10 and 11, we initialize our fast and slow pointers to the head of the linked list. Then the while loop block is the same as what you have for linked list cycle 1. While the current node is not none, then we traverse the linked list. We move one node for the slow one and then 2 nodes for the fast one. And when they meet, we break. But if there's no cycle, which means the next pointer will be none, then we have a try catch for that. We reset the slow pointer back to the head of the linked list. We have another while loop, and this time both pointers move by one node. When they meet again, you can return slow or fast, and that will be your entry node. To prove to you that this code works, I will submit in Leetcode. As you can see, it passes all test cases, and the time isn't the best, but I'm sure you can change the code a little bit to make it more efficient. But hey, 52 milliseconds isn't bad. That's it. I hope everything was clear. Thank you for watching. Comment, like, subscribe if you enjoyed it, and let me know if I should cover more Leetcode problems.